Welcome to Summarize Science, where we break down the latest breakthroughs in physics and cosmology. Today we are looking at a landmark paper that provides a 2% determination of one of the most important numbers in our universe. This number, known as Neff, represents the amount of radiation coming from light, fast-moving particles in the early universe. The researchers used data from several world-class observatories to pinpoint this value more accurately than ever before. By looking at the first page, we see they combined helium and deuterium abundance measurements with observations of the cosmic microwave background. They also integrated data from baryon acoustic oscillations, which are essentially frozen sound waves from the beginning of time. On page 2, the researchers describe using the Large Binocular Telescope to measure helium produced just minutes after the Big Bang. They combine this with data from the Planck satellite and the Atacama Cosmology Telescope to get a full picture of the early cosmos. One major goal was to see if there are any extra particles we have not discovered yet, often called dark radiation. Moving to page 3, Figure 1 shows a comparison of their results against previous measurements from the last decade. Their final value for Neff is 2.990, which is incredibly close to the theoretical prediction of 3.044. This tells us that the standard model of physics is doing an excellent job of describing the contents of the early universe. This result also means there is very little room for mysterious new particles like sterile neutrinos or axions. The researchers found that the cosmic microwave background constraints are now competitive with data derived from light element abundances. They combined all of these datasets to reach the most precise constraint on Neff ever recorded. On page 4, the researchers discuss the physical implications of this tight constraint. They found that any new light particles would have to have been created extremely early or under very specific conditions to exist. This result is particularly interesting because it impacts the ongoing debate about the Hubble constant, which describes how fast the universe is expanding. Some theories suggested that extra radiation could explain why different measurements of the Hubble expansion speed do not match up. However, this study shows that the radiation levels are exactly where we expected them to be, ruling out those simple fixes. It essentially places a very tight wiggle room on models that try to solve the Hubble mystery using dark radiation. Page 5 highlights that this 2% determination is the most precise constraint on these early universe particles to date. The researchers found that their results were robust even when they excluded certain types of polarization data from the analysis. They conclude that the Hubble constant discrepancy persists at a very high level of statistical significance. On page 8, we see complex charts showing how different variables like matter density and expansion speed relate to each other. These corner plots show that the data points from different telescopes all point toward the same narrow range of possibilities. This visual representation proves that the different datasets are in excellent agreement with one another. Page 9 contains the actual data tables, providing the hard numbers that back up these massive cosmic conclusions. In the future, new telescopes like Euclid and the Simons Observatory will push this precision even further. To recap, these researchers successfully combined several massive datasets to confirm the standard model's view of the early universe. They proved that the ghostly particles flying around during the Big Bang were almost certainly just the neutrinos we already know about. This result limits the possibilities for new physics and forces theorists to look for other ways to solve cosmic mysteries. It is a major step forward in understanding the fundamental building blocks of everything we see today. Thanks for watching Summarize Science, and stay tuned for more deep dives into the secrets of the cosmos.